Welcome everybody, this is Vlastimil Kunz, and thank you everybody for making the time to join us and watch this presentation, and I would really appreciate to have your comments when this presentation is done. So what we will be presenting today is a 4-month effort on the part of the Oak Ridge National Laboratory and AlphaStar, and primarily this is the product of AlphaStar's effort. Frank Abdi and his team did a great job putting all of this together and helping us simulate and understand issues that we may be seeing in our big area additive manufacturing process. So this work, I would like to emphasize, is not complete. There is more validation that is needed to really make this technology useful for a wider audience. But I think this is a great start on a long journey. And again, I would like to say that I would like to hear from everybody, hear feedback, whether it's positive or negative, or whether it's just something that's not of interest to you. We just need to hear it, in which direction we should be going and what questions you might have. And so with that, I would like to turn it over to AlphaStar and Frank Abdi's team.
I will start a small discussion about the company AlphaStar Corporations. After that, I will discuss the problem that we were trying to solve. I will show some highlights and discuss the solution approach that we took, and I will conclude the presentation and give some recommendations with respect to the findings that we have found. AlphaStar Corporation is founded in 1989 and is located in Long Beach, California. We are dedicated to provide physics-based multi-scale simulation software for structural analysis for composite materials, but also for other type of materials like metals, ceramics, and hybrid materials. We've done a significant amount of services for both the industry and the government institutions. Our flagship is a software tool called Genoa, which is an addition to classical finite element solutions, where it basically enables the multi-scale progressive failure analysis and material modeling, including micromechanical analysis. We have used our Genoa tool for various of services and for various of industries, including aerospace, automotive, infrastructure, energy, and also for the high-tech electronics. The philosophy that we are using is the multiscale analysis methodology, where we extend the current capabilities of classical and commercial finite element tools by including micromechanical material modeling, where we have a unit cell of the micromechanical structure, in this case a composite, where we analyze the output from a classical finite element solution, and we analyze the behavior on a micro scale and try to determine damage and fracture on a micro scale, and we scale up the effects of these micro damages all the way up to the global structural behavior. And we basically, the software tool Genoa does this in an iterative process in order to enable the analysis of the durability and the damage initiation and propagation within composite materials. The project that I'm presenting right now is a part of what is called the big area additive manufacturing. This is a collaboration of various industry partners, and it's being commercialized by Cincinnati and Local Motors, who is actually printing a full-scale car called the Strati. One of the downsides of these type of manufacturing processes is that a significant amount of material is being deposited in a short amount of time, which basically boosts up the cost of such a production process. In this case, trial and error, which is often used for these type of methodologies, is a very inefficient way in terms of the economics of the production process. So the idea was to come up with a software tool and to come up with a methodology to simulate this process and use the simulations to optimize the production process rather than going through the more expensive trial and error methodology. The problem that we were trying to solve is related to the production process and the thermal effects of these production processes. Now, on your right-hand top, you can see the thermographical images of such a production process. Now you can basically see the contour of a structure being laid, and after that the contour is being filled. And the difference in colors clearly shows a difference in temperatures. And that's basically where all the problem starts with these type of production processes. As you can see here, different layers are put on top of one another, and these layers are referred to as beads. On the lower left, you can see two beads on top of one another being placed by the machine. And you can imagine that when the first bead is cooled down and the second bead is placed on top of it, you get some contractions and deformations due to the shrinkage of the material. Now, because the lower or the earlier laid layers are already cooled down, these contractions or these thermal loadings result in an asymmetric loading case where you get bending in the material or in the structure, and these bendings result in interlaminar stresses, and these interlaminar stresses result in damages. Now, those interlaminar stress buildups in the material or the structure, in combination with the initial imperfections that are already in the material, result in some significant problems in the product quality. As you can see here, some serious delaminations has occurred. This is purely due to the thermal loading during production process. To solve this problem, or actually to address this problem, the following assignment was given to us by the Oak Ridge National Lab, and the idea was to simulate a carbon ABS chopped fiber 3D printing manufacturing process that they are using currently. And the simulation should include the formation of cracks due to thermal loading. The simulation should also include all the parameters that can be changed or altered in order to improve the production process, the so-called design variables. And also there was a constraint in terms of analysis time, which basically said that the analysis time should not exceed a 24-hour period, which is quite a tough constraint because we're simulating an entire car here. The software tool also should be fully automated, which means that the material characterization for the carbon ABS chopped fiber should be done in an automatic way. The model should be generated automatically, including material assignments, material orientations, and damage and fracture assignments. And also the post-processing needs to be automated in order to visualize and address the problem areas. Now let me show you some of the highlights of the results that we got from the tools that we have developed. On your upper left, you can basically see the 3D production process as is simulated in the finite element environment. And on your right hand, you can see the cracks that are initiated due to the thermal loading during the production process. In addition to this, the Genoa software tool enables the analysis of different damage types. On your lower left, you can see all the damage modes that are being triggered during the production process, and the damages also add to the fracture, and this is basically a sequential type of problem that we are addressing. Now, having this tool enabled us to address some of the potential problem areas. In order to visualize these areas, the displacements are over-exaggerated and multiplied by a factor 3 just for the purpose of visualization. And doing so, we can address some problems in the so-called ramp area, where we can see some significant delaminations. We also see some serious delaminations in the front and rear bumper. Also, there are some delaminations where we have some stress concentrations due to some holes that are made for the suspension. And we see some serious delaminations in some of the interior structures, in this case, the mid-console. So this tool basically enables us to show the potential damage areas and to visualize those those problems using the post-processing methodologies that we are using currently. Now let's discuss how we got to these type of solutions. The solution approach is as follows. The code reads in either an STL file or a machine code, which is referred to as the G code, and for the current simulations we basically read in the G code, which was provided to us by the Oak Ridge National Lab. Once the G code is read in, the Genoa GUI will generate a mesh according to the density that it's provided, and also it will include material orientations according to the machine head and fracture behavior between all the layers. In addition to that, there is a material characterization step where we characterize the chopped fiber material, the anisotropic chopped fiber material. Combining these two, we get a full finite element model, which we can solve in different ways, and we have tried different ways to solve this problem. We have tried both uncoupled and fully coupled thermal structural analysis methods, and so far we could conclude that the sequentially coupled solution is the most robust and will give us a solution in the least amount of time. So this is the methodology that we have used so far. Now the heart of this whole tool is the automated model generation, where we start off with reading the G code, as you can see on the top left image, and the visualization of the G code paths enables us to see some potential problem areas already. For instance, we can visualize some bald spots or potential bald spots just by visualizing the parts of the machine head. Using this information, a mesh is generated, including all the material orientations, which are basically included by including the orientations of the machine head. Between every layer, we have a cohesive behavior to analyze and enable us to analyze the delamination behavior during the production process, and also the thermal loadings from the previous heat analysis are also added by the GUI in an automatic way on the model. now this basically enables us to run the problem, and we can generate outputs like residual stresses, deformations, and the crack formations that we have showed you in the previous slides. Like I said, aside from the model generation, we also have a methodology to characterize our chopped fiber material. In this case, we use a tool which we call MCQ chopped, and MCQ chopped basically enables to include matrix nonlinearity, effects of defects in terms of voids and on the fiber waviness. We can include the effects of the fiber shapes and aspect ratios, and the result of the MCQ chop is the characterized material in terms of strength properties and stiffness properties. And in the table we show you the calibrated results compared to the test for a couple of physical tests that were provided to us by Oak Ridge National Lab. Like Vladimir said, we have our goal is to come up with more validation cases and start to validate the methodology to its fullest. One validation case was done already, which is the thermal behavior. Oak Ridge National Lab produced and tested a so-called wall model, which you can see on the top left. And the wall model was produced, and during the production, the thermal behavior was recorded. And we have run our thermal analysis to see if we can get the same behavior as was recorded during the testing. And on your top right, you can see the comparison between what was measured during the testing and the results from our thermal analysis. The image that you can see on the top left is actually the GUI that generates this model using the G-code. Running the model gave us a lot of information about how cracks are initiated and where we can expect the cracks and what were the main drivers of these cracks. And on the lower left, on the lower right, I'm sorry, you can see the crack formations and the location of the cracks. And on the top left, you can see the damages in the beads, which are provided by the Genoa GUI, where you can see which of the failure modes is most dominant and basically results in the most damage within the beads, while the fracture evolution is shown on the lower right. The residual stresses due to the production process can also be used in a post-analysis step where you can include some service loadings. In this case, we have just to show that we can add different loading cases after the production has been finished. We, in this case, have added some lateral accelerations, which is representative to a car going through a curve. And we can show the deformations and the stresses, which are the stresses due to the acceleration plus the residual stresses that are already in the material due to the production process and the thermal loading of that. We initially started with looking at the delamination initiation only, because if you want to improve the methodology of the production process, you are interested in where the delaminations start, and you want to prolong that point as much as you can. Nevertheless, if you want to run the entire problem, in this case the entire car, there is an effect of fracture growth or delamination growth that needs to be accounted for, and I've tried to make that clear in the images that you can see on the bottom of this slide. As I mentioned, you have the asymmetric loading due to the thermal effect, causing delaminations due to the interlaminar stresses. Now, if you look at this as a pure bending problem, you would expect a transverse shear stress distribution as is shown in this image. And if you just only look at delamination initiation, this will basically just start building up, and after the first delamination initiation that is occurring in the structure, anything after that becomes less reliable, because in reality, once delamination has been initiated, propagation of the delamination will also start, which means that the compatibility between the adjacent plies is removed, which results in a stress relief. So the stress pattern or the stress state of the structure after the first delamination initiation or delamination growth is altered and is different than from the situation where you would only look at delamination initiation. For this reason, we also included the delamination growth or fracture growth in order to have a more realistic simulation of the entire process. To conclude this presentation, we have created a mesh generator which can read either an STL file or a G code to generate a mesh including material orientations and fracture behavior between all the layers, and also the thermal mapping from the initial thermal analysis. We have characterized our chopped fiber material using coupon tests that were provided to us by ORNL. We managed to validate our heat analysis or thermal analysis process using the wall model that was also provided by ORNL. We have included some design parameters that can be changed to improve the manufacturing process. This can be like printer speed, material temperature, ambient temperature, fiber length, material type, etc. We have the software that we have developed enables different solution types, both fully coupled as well as loosely or sequentially coupled. And the methodology finally allows the predictions of residual stresses, deformations, delamination initiation and growth, the failure type and location of those failures, and this is all basically done in an automated way to simulate the production process. There is still a lot to do. Like Vladimir already mentioned, this is just a 4-month effort. We are very much dedicated to get this methodology to the next level and start the full validation. And we prefer to start the building block validation strategy, where we start off with ASTM standard test on the coupon level, and we increase the complexity all the way up to the full-scale analysis and test level. There are some initial material defects that need to be included, and also for that we need some additional testing in terms of fracture tests on a structure rather than on a material. There are some plans to expand this methodology to other material types or material systems, like thermoset materials, where we want to include aspects like curing and distortion due to curing. Also, we produced this methodology using the Abacus finite element solver as the FE solver, and we want to make this tool available for different solver platforms like ANSYS, LS-DYNA, or Radials. Also, we need to get a better representation of the geometry. Currently, we can do that, but that would require a significant amount of mesh, which will boost up the analysis time significantly. So we are working on getting more intelligent ways to come up with a better representation of the geometry of the produced process or the produced product. I really want to thank everybody for their interest and for the time. If you have any questions regarding any of these subjects, please don't hesitate to call either Dr. Rashid Miraj from AlphaStar or Dr. Vladimir Kunk from ORNL, of which you can find their contact information on this slide. Thank you very much for your attention.